record. Okay. Okay, I already have uploaded your new laboratory exercise for decision trees. That's the first lab exercise. That's only for Boolean functions, so that's will be very easy for you. And then the second one will be after this lecture, we will have another exercise. So that means almost every week we will have a laboratory exercise for you to practice in computations. So that's the second topic. And then the third topic will be Bayes rule. And so after Bayes rule, we'll have your long test, first long test. Okay, we're almost there. Okay, and then if the university extends one more week, I think we'll finish early because we never miss lecture classes. So we don't need to follow the extension of 1 week because we never lose any time. So that means that we can finish the class earlier than everybody else. Okay, especially those who didn't. Most other lecturers are still doing face-to-face classes, and so those for sure they were disrupted by the events. I don't want to mention because this one. Okay, so for us we were not affected, so we can finish early. Okay, so let's move on, and then I will share my screen. Is my screen shared already? Not yet. So let me share my screen and share. Okay, now let's continue with decision trees. Okay, so this is let's view presentation. Okay, so I think we stopped somewhere. Where did we stop? Somewhere here or no? I think we stopped in entropy. Okay, never mind. Let's start from here. So how do we, the problem that we were discussing or that we were addressing last time was that when we are doing splits or we are doing branches for a given node, for example, we considered, let's go back to here, the Boolean functions. So for example, if you have a Boolean function where in this case, phi is equal to not A and C and then B, all these things, then we create a Boolean table. And then using that Boolean table, we can create a decision tree. So in this case, there are two possible decision trees, this one to the left and the other one to the right. Okay, but then in this case, because the Boolean function is commutative, that means we can interchange them. That means it doesn't matter whether A is here or B is here. We can interchange A or B and C can interchange them. So that means that there are many other possibilities of a decision tree. For example, this is one possibility and the other one is this possibility. And of course, you know, with lesser computation, it will be nice if the trees are more compact. That means less nodes and less leaves and less branches because there will be less computation. So in this case here, the left side is much better than the right side because it can reach a decision very fast, much faster than the right side. So the right side in this case is only simplified on one branch. And so we have to go through all these routes, all these paths in order to reach a decision, which we call leaves. Okay, but then for more complicated things like this, there is a way to determine what will be the layer in the decision tree that you would want to use. Okay, so for example, in this case, a decision of the miles per gallon, which is the car model that has better miles per gallon, given the information about number of the cylinder size, I think number of cylinders, the displacement, that's the size of the displacement, horsepower, weight, and everything, acceleration, model year, and the maker. Then it can determine whether the miles per gallon is good or bad. I mean, this is a US or some European examples where people are really concerned about how much gas they use. Well, they like to drive, of course. You'll get you have to spend gas because you like to drive. There's not much of public transportation. So anyway, so again, we are looking at a function f given the input x. In this case, the input are these x X's, the parameters, cylinders, displacement, horsepower, weight, acceleration, model year, and maker. Those are the input X, and then the output Y is the miles per gallon, whether good or bad. So what we need is something like this, a tree, a decision tree, that determines which one in this, this is the attribute or the parameter, and the number of the cylinders, 3, 4, 5, and 6, and it can decide whether good or bad. And then from there, we make another node of the maker, another node of the horsepower. Then the question is, how do we choose those nodes? Okay, so we say that we choose them. Okay, which nodes will come first? That's the question. Why do we choose, in this case, in this example, cylinders to be our root node and not the maker? Okay, or the horsepower parameter. Okay, so to choose those, there's a way of choosing them, and we say that we split. In this case, we can split based on the X and Y, X1 and X2, and then of course there's other depending on the output. The output, whether you choose X2, then you have different outputs, and then if you choose X1, you have different outputs as well in terms of true or false. So in this case here, there are possibilities, other possibilities of which one you choose as your node and which one you choose is node, which one, when you choose a certain parameter, there are possibilities of probabilities, changes in the probabilities computation. So now it brings us to the point of entropy. So we say that entropy will give us some measurement of which parameter we should choose as the first priority in terms of node, and then which other parameters will come second. Okay, so first let's consider the entropy. We say the entropy will tell us about the certainty of certain parameters, certainty of whether a yes or a no, or certainty of a certain aspect. Yeah, and so the higher the entropy, the higher is the uncertainty. And so in this graph here, if a coin flip, a probability of getting head, if you really get head, that means the entropy is 0, because definitely you got a head. Okay, and I mean, sorry, at the tail. Yeah, tail is normally 0 and the head is 1. So if you get a 1, definitely you get a 1 and the entropy there is 0, because that's a definite answer. But if you're somewhere between those, then there's a high, the entropy is very high, because there's a 50-50, for example, here, the 0.5 probability, there's a 50-50 chance of you're getting head or tail. So the entropy is very high. So what this method is trying to do is that we measure the entropy, and we'll get 10 more minutes. We'll measure the entropy, and we take the one with the highest entropy. The highest entropy will be the layer that is the highest priority. Okay, so now the entropy is just the output, probability of the output of the Y. In this case, for example, yes or no, log 2 of probability of a yes, for example, and then plus probability of no, log 2 of probability of a no. Okay, it will be much clearer when we get into the example. So in this case here, if you are given a table here like this, so we'll just count. Okay, we counted. Okay, what was it given here? Yeah, we count the yes. In this case, if you're X1, and then if you're X1 and you consider only the true, then in the true you get a yes that is 4, and the Y output, sorry, the Y output is true, and that is for all the X1 that is true, the Y are all true, and there are no false. Okay, so that's 0. And then for X1 that's false over here, you have 1 that's true, and then the false is 3. Okay, using that, also we did that information for X2. So using that information, we can compute the entropy. For example, in this case here, this is the overall picture for the overall entropy, the probability of the yes and probability of the no. So in this case here, probability, the true or false, yeah, yes or no. Probability of a true, in this case, how many are true? So in this case, 1, 2, 3, 4, 5. 5 are true of all the other outputs of Y, 6. So 5 over 6 is true, and false is 1 over 6. So now the entropy H of Y of all the possible outputs, they only have two possible outputs in this case. Yes, true or false. And so you just substitute there, minus 5 over 6 like to 5 over 6 minus the additional case, which is the false, minus 1 over 6, and then the entropy is this one. Okay, so now that's our, if we consider now the example of in this case here, there's another term that we want to consider, the conditional entropy. Okay. Conditional entropy, I think we stopped from here before. Conditional entropy is considers, first one is this absolute entropy. It's not conditional. This is just about the output. Okay. The second entropy that we are trying to consider is the conditional entropy. Given y, okay, given y, what is the parameter x, okay? So given y the output, okay, given y the output, so in this case y output can be true or false, and then the parameter x is x1 or x2, okay? So that means that in this case here, I goes from, in this case, I, okay, I is the output, okay? The y, there are two possible outputs, yes or no. So that means this one goes from 1 to 2, okay? And in this case here, j is the parameter, okay? How many parameters you have? Okay, how many parameters you have? You have you choose the parameter, x is the, okay, sorry, x is the parameter or the attribute. This is a little bit confusing because in this case here it should be h of y given y, the h of y given x, given x1, okay, h of y given x2, okay. So in this case here, given x1, so if this is given x1, so we will have x1 can be true or false. Okay, I should do that. I should correct this one because it's not complete. Anyway, it can be confusing. So okay, let's go back. So given x1, so it will be clear, and x1 and x1 and x1. Okay. So we know that y is true or false. We already know that. So in this case, x1, okay? Condition, the y, the output y given x1. So we consider x1. So in this case here, how many possibilities of x1? There are two possibilities, true or false. So that means v is equal to 2 because that's true or false for x1. And then k is also 2 because there's also true or false for y. So that means that if you consider this, there's another conditional entropy that is not shown here. For this particular table, you have another conditional entropy that is y given x2, okay? So in that case here, you have x2, and then you'll just have the same equation and then substitute in terms of x2. Then y is the same because the output is the same. So now, how do you compute the conditional entropy given x1? So probability of x1, probability of x1, because this is what we are looking at, probability of x1, okay? That is, x1 has two possibilities, yeah, true or false. So now, x1 being true, that is 1, 2, 3, 4, 4 divided by how many instances of x1? Okay, there are 6. So 6, that's 4 over 6, and the false is 2, that's 2 over 6. So this one here, this part goes to here. Okay, so that means that, so given x1, you have true, and then you have false. This is the absolute entropy, okay? I mean the absolute probability. And then the conditional one is that given x1 and true, okay, given x1 that it is true, then we consider only this one. Okay, so how many are true? That's 4. And how many are false? That's 0. That's correct. and then given x1 to be false, and then we consider again this one. So 1 is true and 1 is false. Okay. Now we can compute this. Okay. So we first compute this part here, this part, that given x1, okay, x1, given x1, okay, given the output x1 to be true, okay, x1 to be true there, okay, and then you have given x1 to be true, and then what is y x1 to be true, and then what is y1, okay, and then y1 you have true or false as well. So we consider first the true, that is 4 over 4. So this is, I should have written it before, 4 over 4 log 2 of 4 over 4, okay, because that is the true. Okay. Y, that means in this case here, this is the y that is equal to true. The yi is true. Okay. Remember, this is a summation. Okay. So that summation will give us that first. Okay. The true case, because in this case, xi remains, x1 remains constant because it is outside of the summation. Yeah. So x1, in this case, we consider only x1 that is true. Okay. So x1 that is true, only this branch. So this is 4 over 4 log 2 of 4 over 4 plus 0. There's no other part here. Okay. We don't do 0 over 0 because that's not defined, but that is 0. So in that case, that is the 1. And so 0 log 2 of 0, this is undefined. So now we consider this part. So minus, so we multiply it with probability of the, in this case, the x1 to be true. Probability of x1 to be true, in this case, that is that one. So this is 4 over 6. Okay. So 4 over 6 multiplied by this when x1 is true. So x1 is true. That's 4 over 4 plus 4 over 4 log 2, 4 over 4 plus the other case, 0, 0. Okay. We don't do 0 over 0. Then the next case is when x1 is false. So when x1 is false, you have 2 over 6 plus, okay, now x1 is false. What is the possibility? That is the true case. So that's 1/2 log 2 of 1/2 plus the false case, 1/2. Again, this case is here inside, 1/2 log 2, 1/2. Okay. So now this whole case is